So I used to use the word friction in here, but have I told you why this is not friction?
Yeah.
Friction depends on like a normal force squishing two things together and the type of material. It doesn't depend on speed. It doesn't depend on density of the surrounding medium or any of those things. So drag is a different kind of an animal. So drag is a force resisting the motion of an object through a fluid, or a force resisting I'll say that, the motion of an object through a fluid. It could be the reverse too. It could be resisting the motion of a fluid around an object. So you could imagine throwing a frisbee through the air, or you could imagine holding a frisbee still and blow an air over it. And in both cases, the drag is going to be doing the same thing. It's pushing on the frisbee and pushing on the air. And the drag force equation we kind of derived earlier. Drag equals, what did I say most special formulas begin with?
1/2.
Yeah, it seems like all the really cool formulas begin with a 1/2. And then there's A, which was what? You remember?
Area second.
Cross-sectional area. This is the cross-sectional area that's exposed to the oncoming wind. But I'm not going to write that. I'm just going to write cross-sectional area. So you can be really big, but as long as you just point your tiny parts into the wind, then you don't have much drag. All right, so moving on. So then there's this other one that's coefficient of drag. This is a measure of aerodynamics. And the shape that I showed you earlier that has the lowest coefficient of drag is what? Teardrop, airfoil. It's like the cross-section of an airplane wing, sort of. And then, what's something else that's in here? So the one that looks like pressure, but it's actually a rho, which stands for what? Density. So this would be air. This is the density of the fluid. By the way, what is a fluid? Does a fluid have to be a liquid?
No.
Does it have to be a liquid or a gas?
Yes. Wait.
Can other things flow other than liquid and gases? Corn? If you have a bunch of dried corn in a silo, that can kind of flow. Sand can flow through an hourglass. So it really, a lot of these things can have drag too. So it's just, a fluid is something that can flow, but it's usually a gas or a liquid. And then the other thing is velocity, and that's velocity squared. Okay, so now some diagrams of skydivers. You can draw your skydiver how, oops, why did I do that? Oh well, that's the backpack. Okay, that's the backpack. And that's the backpack again. And I'm not going to draw the third one. I'm going to draw, yeah, I'll draw the third one. This is a skydiver. What does it look like to you?
Like
Okay, Bug. It's a person. It's a happy skydiver. How about this?
Oh.
The last one should be scared because he has no parachute.
All right. So the
Is the third one not have a backpack?
sort of.
Those are backpacks?
So like I do need to.
I guess maybe I still need to draw the backpack. Okay, I'm drawing the backpack again. They're supposed to be the same skydiver over and over. Yeah. So this is going to be negative acceleration. This is going to be zero acceleration. This is positive acceleration. These are sort of some stages of skydiving, and then we'll get in. I've never skydived. Okay. Have any of you skydived? I'm not going to skydive. I don't think I'd want to.
It would be
Terrifying. I think it would be terrifying. So in this first one, the skydiver has negative acceleration. Why would somebody have negative acceleration?
Because of gravity.
Because of gravity, but is there no gravity at these, like, Is there any point in your skydive where gravity goes away? No. So there's always, in fact, let's go ahead and draw the force of gravity every time. That shouldn't change. Now, what's the name for the force of gravity? Weight. And if you wanted a little formula for it, it could be mg. So I'm just going to write weight. And just for the fun of it, does anybody want to propose a weight for this skydiver?
200,000 kilograms.
I heard 200 before. Was that pounds? So 200 pounds is somewhere around 800. Let's just do 800 newtons. 800 newtons. 800 newtons. 800 newtons. Just to give us some kind of a reasonable reference. So back to why the acceleration's negative. The weight is always negative. There's always the weight pulling down. But the weight is, or the acceleration is going to be 0 here and positive here. So maybe I should say, why would the acceleration be 0 here? Because, yeah, sorry, Chris?
The opinion side.
Yeah, there's not just this force. If there's 0 acceleration, what's the net force? Net force equals ma. Assuming they have some mass, if there's 0 acceleration, what's the net force? 0. So if the net force is 0, then this force has to have another force perfectly canceling it out, and that's drag. We'll just do a D for that. So what is the drag force here? How many newtons? 800. Okay, so if we've got negative acceleration, what does that tell us about the drag force? It's less. So I don't know. Let's just make it, let's say drag is 500 newtons. So what's the net force acting on this skydiver? Yeah, net force is, I'm just going to do 300 and use an arrow, a down arrow, 300 newtons downward. Sorry, I don't like the way I did the arrow and then the unit. 300 newtons downward. And so if you wanted to, you could say that equals their mass times their acceleration. You could figure out how fast they're accelerating downward. And why would the drag be smaller here than it is there? What causes your drag to change as you fall? What part of, yeah, so the velocity goes up. So assuming that the density of the air is the same, which isn't really true. The lower you get, the denser it is. Assuming you keep the same shape, that you're not tucking or anything, assuming you stay the same size, this is what's really changing things. So as you fall faster, drag increases, and at some point the drag gets to be the same as your weight, and then your net force is 0, so your acceleration is 0. So do you fall faster, slower, or the same speed? Same speed. If you're going the same speed, can your drag change anymore? I mean, if you keep all these other things the same, and you go the same speed, then drag can't change. And that's why this is the name for this. Let's go ahead and write it here. Terminal velocity. When a falling skydiver's net force and acceleration are 0, he or she is said to be at terminal velocity because this is the last velocity you have. It's terminal. It's the end. You're done accelerating, whatever velocity that is. If you don't have a parachute, it's 120 miles per hour, roughly. So you reach terminal velocity where the acceleration is 0. Now I'm saying we have positive acceleration. How can you possibly suddenly have positive acceleration? You pull the chute, and what does that do? It sends this thing up here, and what does that change mostly in this equation? Two things, really. A would go way up, and what else might change? Maybe your coefficient of drag would change a little bit too. Hopefully your parachute is some sort of a shape that catches air and it's not you don't want an aerodynamic parachute.
What if you had like
a person-shaped parachute? That could still slow you down as long as it's a big person-shaped parachute that isn't. That'd be kind of funny, actually. That if I did skydive, it might be so I could just make myself a person-shaped parachute. But anyway, so let's say that the drag, what should we use for drag now? We had 800 newtons, we had 500 newtons. 1,000 newtons. I'm going to go bigger. I'm going to go 2,000. Drag equals 2,000 newtons. I wrote 200. According to our former head of security here, who used to do a lot of skydiving, this is the most painful part of skydiving. When you open up your parachute, it really jerks you upward. The acceleration you experience here is stronger than any other acceleration. So if this is 2,000 and that's 800, what's the net force? It'd be 1,200 newtons upward, which is stronger than the force you would experience if you just let yourself free fall downward. If you had no drag, the moment you step out, you wouldn't be experiencing that acceleration. That's probably too low. The jolt is much stronger than that. All right.
Wait, how many tons of force?
We could look it up. So let's see. Force experienced when parachute opens. What does the AI say? Significant. Oh, come on, that's weaseling out. Upward of 3 Gs, just pull from the parachute, counters the natural pull of the earth, causes them to experience upward of 3 Gs as they slow down from 120 miles per hour to 15 miles per hour. So I don't know, 3 Gs isn't that. I would bet that's probably after it's deployed. I bet there's a really strong jerk before that. Maybe maximum force. Ask, yeah. So this is still going to give me the same thing. Oh well, that's a rabbit hole I need to pull my head out of. All right, moving on down. We're not going to need this yet, but we're going to need it when you're going to make a spreadsheet for actually determining the drag effects on something. And to do that, we need a formula for terminal velocity. We're also going to answer the question, if I shoot my AK-47 straight up in the air, or my AR-15, or my shotgun with number 2 shot, or my cannonball, and then I let it fall straight down on my head, what will it do to me? So we can use this formula to figure it out. So we need a formula for terminal velocity for this V right here. And at terminal velocity, what two things are equal? Drag and weight are equal. What's the formula for weight? mg. What's the formula for drag? 1/2 times capital A times C sub D times rho times V, times V squared. So at terminal velocity, I'm going to write it over here, at TV, weight equals drag. So this is just making weight equal to drag. And of all these letters, we've got mg, a, cd, rho, v. Which one of those is the terminal velocity? That's the v. This is the v we're looking for. So I just need to solve for v. So I'll do this in a couple of steps. I'm going to multiply both sides by 2 and divide both sides by what? A, C, D, and rho. So let me just write my mg multiplied by 2 divided by A, C, D, rho, and that equals what? V squared, but I'm just going to kill it all in one step. V equals square root of all that. So this is the formula that we'll use later on. If you wanted to know if your AR-15 bullet, you're really happy and you just shot it up in the air to celebrate, you'd multiply the mass of the bullet times 9.8 times 2, divide that by the cross-sectional area of the bullet. You'd have to decide, is it going to be spinning and going point first, or is it going to be tumbling end over end? I don't know. And then you'd have to divide that by whatever the drag coefficient is of the bullet, and then divide it by 1.22, which is the number of kilograms per cubic meter of air. And then you could get a velocity. I've done this. I've got a spreadsheet, so we can put in different things and see how fast they would fall down on your head.
Wait, how much does a bullet weigh?
It varies.
It's like a 5.56.
Well, tomorrow. No, the day after tomorrow, I'll show you. I'll share my spreadsheet. You can look ahead on my website if you want. Flip to the next page. 20 minutes. Dang. Okay. I'm sorely tempted to cut corners on this. So I'm gonna kind of do this a light version. I got out a sheet of paper thinking I was going to draw on it, but I'm not. Okay. So all we've got to do here is show the accelerations acting on a skydiver. It also says to do some other drawings. Maybe we'll skip that. Okay. So skydiver steps out of a helicopter. Skydiver reaches terminal velocity, negative 40 meters per second. How many miles per hour is that? 2.24. That's not as fast as the 120 miles per hour. It's around 90 miles per hour. I don't know. They're fluffy, I guess. And then the skydiver pulls the chute cord, the parachute deploys, and they reach a new terminal velocity. Then their feet touch the ground, and they come to rest. Okay, let's just start drawing acceleration. So as soon as you step off a helicopter, I am going to draw over here. Why a helicopter? Why not an airplane? Yeah, I didn't want to have to deal with the other motions. So here's somebody, there's a skydiver. They step off. They're right here standing in space. What's the acceleration of the skydiver? Negative 9.8. They're going to start falling, and as soon as they start to fall, then air is going to push against them, and they're going to have drag, and it's not going to be 9.8 anymore. So after a little while, as they fall, like right here, so here, I'll just do these drawings. In the beginning, there's just weight pulling down and no drag. And then on this person, there's weight, but there's a little bit of drag. And then eventually, what's going to happen to the drag force? Eventually the drag force is going to equal the weight, and the net force is going to be 0. So I'm going to write net force equals the weight. Over here, net force equals a smaller little force downward, and then 0. What do we call this moment in time when something is, missing it. So this is where they've reached terminal velocity. So on this graph that we're about to draw, I want to show what's happening to the acceleration between here and here. And let's say this is where they step off, this is where they reach terminal velocity. What's the acceleration right when they step off? Negative 9.8. What is it when they reach terminal velocity? 0. So would you guess this is linear?
No.
It's really more like this. And yeah, the explanation for that is the closer you get to your terminal velocity, the slower you're accelerating. So terminal velocity is the point where you're not accelerating at all. So the closer you get to it, the closer you get to it. And really you sort of approach it asymptotically. So this is reaches TV number 1. And this is steps off. And all right. And right here, I'm going to label this. Which one's greater, weight or drag in this region? Weight, yeah. Instead of a big drawing, I'm just going to do weight is greater than drag. And then at terminal velocity, what's going to happen to the acceleration after that? It's going to stay 0 for a while. Until what? till they pull the chute. So they reach terminal velocity and then they fall at negative 40 meters per second for a while until they pull the chute. So let's say they pull the chute right here. During this time, when they're at terminal velocity, how do the weight and drag compare then? The weight equals the drag. All right. Then they pull the chute. Let me go back to my picture. Here they are. Suddenly, there's this big chute up here. The weight is going to be the same. What happens to the drag? Gets really big. So which way is the net force? Upward, which means the acceleration is upward too. So right here, there's this big yank like this. And this is the chute deploying. And during this time, how do the weight and the drag compare? Drag is greater than weight, or you could say weight's less than drag. I'm going to do drag is greater than weight. And this is the kind of weird part. So as you fall faster, drag increases, increases, increases. Then it gets to be the same as your weight. Then they're equal for a while. And then you open up your chute, the drag increases and it's higher than your weight. So you get an upward acceleration. But then the drag decreases again. Does the chute go back in? So why does the drag decrease? Because you're slowing down. So right in this area and in this area, both of those times the drag and the weight are equal. So this is terminal velocity number 2, and weight is equal to drag again. But the way that the drag gets its strength is different. Here, it's equal to your weight because you're going really fast. Here, it's equal to your weight because the cross-sectional area is really big. But in both cases, those forces are equal. This is a much better situation to hit the ground in. So then finally, you do hit the ground. And when you hit the ground, which way do you accelerate, up or down? Up. So there's this one last push. And just to, let's see, just to show what's happening here, let me fill in what I've left out. So here's the person still with the chute open, but they're now slower, so the weight and the drag are the same. That's what's going on right here at terminal velocity. And then they hit the ground. Let's just say they're not really paying attention. And they hit the ground like this, and the chute is starting to go. What force pushes against them? The ground. So the normal force, and that's got to push harder than the weight, and the net force is upward. Net force here was 0.
Normal force pushes up with more than the weight.
Mm-hmm.
They bounce back up.
No, it means they're going down, but they're accelerating up, which means they're doing what? Speeding up or slowing down? They're slowing down. So they have an upward acceleration, but they still have negative velocity, so it slows them down. So last, I'm going to just write normal force is greater than weight. And then right here, weight equals normal force. So this would be, you're standing on the ground. I'll draw the person here. They've gotten back up. They've recovered. Normal force is pushing up. Weight's pulling down. They're just at rest. So you've got a good 13 minutes to do a few things. First, I challenge you to do this. This is going to be a little tricky. And I'd be happy to help you, but it's a tricky one. Number 5 on page 15. There's a watermelon dropped out of a plane at time 0. It reaches its terminal velocity of negative 100 meters per second at 20 seconds. It hits the earth at 500 seconds. You've got to fill everything out for the watermelon. And remember, there are 2 ways to get net force. This is the important thing here. What's one way to get net force? MA. What's the other way to get net force? the sum of the forces. And the forces that are involved when something's falling, how many are there? 2. What are they?
Gravity.
Which is the watermelon weight and drag. So normal force is only when it hits the ground. And these times are before it hits the ground. So if you're thinking about adding up forces, these are the 2. If you want to do F equals ma, here's the acceleration, and you're given the mass of the watermelon, 10 kilograms. So there's that, which is tricky, but once you get the hang of it, it'll be easy after we practice it a few times. And the other part of the homework is to do 4, 5, and 6 back on page 11.
Like the melon thing's part of the homework.
What's that?
The melon thing's
Yes. Yeah, so the homework is page 11, 4, 5, and 6. 5 and 6 really go together. And then the watermelon, page 15. And that's it. Got 11.